Good afternoon, everyone, and thank you for attending our Heavy and Extreme Copper PCBs for Military and Aerospace Applications webinar. My name is Kendall Paradise, and I'm the president of Epic Engineer Technologies. Before we get started, I just wanted to let you all know that you'll be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel located in the webinar control panel, and we will try to get to them all at the end of the presentation. Also, we will be recording this webinar and we'll be posting both the recording and the slides on our website and YouTube channel. Our presenter today is Al Wright, our PCB Field Applications Engineer. Al has been in the printed circuit board industry for over 35 years and has been with Epic for more than 15. As a field application engineer, he handles a wide variety of responsibilities, including reviewing PCB designs for manufacturability during quoting and design, interacting with off-site manufacturing facilities to solve technical issues during production, and programming CNC machines for in-house projects, reworks, and modifications. Al's technical expertise is essential to our engineering department and provides valuable insight when working with customers. In Al's career, he's worked with over 50,000 different printed circuit board designs from 1981 through present day. He works with our team and your team to get all the designs right ahead of time so the product will be correct the first time through. And with that, I'm going to turn it over to Al.
Hello, everybody. As Kendall said, we'll be going over some heavy and extreme PCBs, specifically for military and aerospace. We also build them for commercial purposes. First off, we'll give you a little overview of the product. Standard commercial PCBs are typically built to perform for a relatively short time and in relatively controlled environments. We all know about planned obsolescence. Things are timed to wear out quickly. PCBs for military and aerospace applications, on the other hand, really have to be able to operate for years and often while exposed to extremes of temperature, altitude, and vibration, and other bad things. Maximum reliability, therefore, is essential, and Epic has the experience in building this type of board for a variety of critical high-power applications, from nuclear submarines to drone aircraft. So the agenda will be to first go over how we categorize different PCB types by copper weight, then just some very basic heavy copper fabrication techniques or options. Then what I'm going to do is branch off, and rather than go through every possible iteration of design choices that you could make, I'm going to show you about a half dozen boards we've built with that solved certain problems for the customer, and that may get you thinking about ideas for your own designs. Then we'll go into overall cost versus reliability, getting a quote, which will include processing, cost adders, and expectations, then planning your project, and additional resources at the end. So first off, we define the PCB types. First type is no mystery, standard copper, 1/4 ounce to 4 ounce. These boards are, they've been built for years. Everybody knows how to do them. Heavy copper boards we define as being between 5 ounces and 19 ounces. These present some additional challenges, but where the copper is the same weight on every layer, once you get used to building them, they can be pretty repeatable too. Extreme copper boards are defined as anything between 20 and 200 ounces per square foot. Now these require some special techniques and processing, and they really need to be thought through very thoroughly early in the project in order to get them right. And the last one is an interesting product we have called PowerLink, and this is when you have 2 or more copper weights, generally one standard copper weight plus another heavy or extreme copper weight on the same external layer. And we'll go into that in greater depth because that's a very useful product, and a lot of you will probably be interested to hear about that. Now the basic ways that you process heavy copper are that you can do an additive plating process, which means you define the circuit on light copper and then you use electroplating to plate up to the final copper weight. Now the pros of this process are that you get a very well-defined trace edge. You can see from the diagram on the bottom that it's very perpendicular. You can also get finer traces and spaces because you're etching through less surface foil, so you don't get problems during the etching process. The cons of this process are that it's more expensive because it's time intensive, and in some cases of very extreme copper weights, rather than photo processing the circuitry, we will do some CNC machining to form the circuitry. So that can also be a little bit costly. The subtractive process is basically printing the circuit and then etching it. The only real pro to this is that etching costs less than plating. So you can start with a heavier copper weight, maybe bond some 10-ounce sheet stock to some FR4, define it with a photo, and then etch it. But the cons are that the trace is less well-defined, and the cross-section ends up being a trapezoid rather than a rectangle, and it requires larger traces and spaces because you're etching through a lot more copper than you are using the additive process. Now, power link is when you have the multiple copper weights on a single layer. Different areas are plated to different copper weights, and this is so that you can combine a power section with a logic section all on the same layer. It's typically used on external layers only, and the lighter copper areas permit component soldering and higher density devices. The beauty of that is that when you're soldering the components, you don't have all that extra copper acting as a heat sink and potentially causing you to damage the components while you're soldering. This is a multiple stage additive process, and if you look on the diagram on the left here, the photo on the left, you'll see that the trace edges are very well defined on these heavy copper traces. You'll also see that there's a light copper area of about 2 ounces, and then there are actually 3 additional copper weights plated in different stages for 10, 20, and 30 ounces. The board on the right just has a few through-hole devices where my mouse is hovering, little connectors, and the rest of the board is 20 ounces. So you have a 20-ounce area for most of the board and 2 ounces here. So again, that really has some benefits for soldering, but you still get the high power section. So going into the individual advantages that I told you about, we're going to go through some examples of individual boards that have particular advantages or problems that we were able to solve for a customer. This board here, one of the advantages is mechanical durability. You can see that there's quite a bit of surface copper in those plane areas in those 2 photos, and that adds to the overall mechanical strength of the extreme copper PCB. And then another thing you can do, if you follow my mouse here, is we have a mounting hole here, but we also have a series of 5 vias, which can not only be used to conduct electricity, but they can also be used for mechanical strength. By drilling those holes and then plating them, when you go to bolt something down into a hole like this, instead of compressing the FR4, these vias resist the force and prevent the FR4 from being cracked or fractured during that process. So that's one little trick you can use in areas where you need to mechanically attach devices. Another advantage that was solved with this particular board is reduced layer count. This is a power link PCB, and there's just a few 6-ounce copper traces in red on the top and bottom layers with 1-ounce surface mount control section. So an earlier version of this, when we first saw it, form these connections by using parallel 3-ounce internal signal layers on the top and bottom. The result was an 8-layer PCB, and they weren't really getting great performance out of the board. They were still getting a little overheating problem. So we suggested they move those to the external layers, and they were able to get down to 4 layers, and now they had the 6-ounce traces were now in air rather than being encapsulated in the internal layers, which gives them superior cooling characteristics. Traces on internal layers tend to have to be derated by, as a rule of thumb, about 50%. But when you have them out in the air, they just cool more efficiently, and they were very happy with this solution, and we've built about 5 different part numbers like this for them. Package size reduction. This board, again, combines a power link structure of 2-ounce control section and 12-ounce power section on different areas of the same surface. The heavy copper replaced some additional wiring that was being used in these areas. And another thing that heavy copper can eliminate is the need for bus bars. You don't necessarily need to add bus bars afterwards in some cases. That's another savings in assembly time and package size. And there's a potential increase in long-term reliability, because that copper just stays bonded to the board. There's really not a whole lot of ways that it can fail. Here's another advantage of extreme trace thickness. This is a 3-layer board with 120-ounce copper internal traces, which you can kind of see they're embedded in the board, the darker areas. These are pre-machined and embedded into the internal layer structure. So we cut out the internal FR4, we drop those in, laminate everything together. Then on this particular board, we have the additional feature of routing down to the internal copper and then plating up these terminal areas to an additional 7th thou above the surface of the board. It's a very tricky process, and a lot of trial and error was involved in getting it right, but it's right at this point, and this board has been functioning for a couple of years now, and it also has these 2-ounce copper areas over here for a few resistors and caps. And again, you'll note that they're not in heavy copper areas. They're out in the middle of the board, so they stay nice and hot when you go to solder them. They don't, the heat doesn't sink away, and you're able to assemble it without burning up the component in the process. Now, I want to touch on costs versus reliability. Heavy copper boards do require extra processing, and they require extra materials that add costs. They're not in the same pricing structure as normal boards. The costs can include long plating cycles, multiple film resist applications, and multiple solder mask coats. Multi-layers typically require extra plies of pre-preg as well. You need to weigh these costs against the previously listed advantages of heavy copper, including long-term reliability, probably being number 1. EPIC will work with you to quote your project so that you can weigh your options before you commit. Now, the quote cycle turnaround time is a little bit different for these boards too. Every heavy and extreme copper quote requires a full design review, and this is because each design is to some extent unique, and it doesn't really lend itself to checklist style pricing that's used for normal boards. Some orders we find require purchase of at least some custom materials or custom processing, for which we need to check availability. We almost always like to discuss the project with the customer unless it's really, really completely defined at the beginning, so that all the requirements are captured. That way we get you an accurate price, and we have a good idea what we're up against. And then the quote cycle, therefore, takes from a few days to sometimes even a week or more. So again, it's not something we can just throw it in a spreadsheet and spit something out. In a lot of cases, it does require some extra effort. Some of the other cost factors that I didn't touch upon before, small run prototypes sometimes need custom materials, and if the custom materials are subject to minimum order quantity pricing, that can really boost the cost of the project. They require special processing and equipment, things like planarizing, special machining, so forth. Plating, imaging, etching, and lamination cycles are often very long, and they can consume more materials than usual. That's probably especially truest with the plating and the photoresist. Because of these factors, it's important to remember that EPIC won't be able to do quick turn build cycles on these. These boards kind of take as long as they take to build. There's really no shortcuts. Most orders require about 20 to 25 working days to produce, not including ordering time for special materials. And down below, I've just shown a lamination scheme where there's a little bit of extra processing compared to a normal lamination scheme. So we do recommend that, or we do encourage you to engage in the EPIC quote process, and we ask, what can you as the customer do to get your quote in a timely fashion? First and foremost, ask us for recommendations early in the cycle about optimizing your design choices. The more advanced your documentation is, the faster we can quote, but even if you don't have anything advanced and you're just looking for something budgetary, if you have a basic concept drawing, that can be extremely valuable, picture being worth 1,000 words. Let us know your expected quantities, too, for both prototypes and production. Sometimes in production volume, factors like larger material buys can significantly reduce pricing, and we might be able to roll a prototype and a production order in and give you some kind of a price break on the prototype, so that you're not paying the freight for all kinds of minimum order quantity pricing and getting really slammed. So again, recommendation, plan ahead and budget your time. Plan your project as far in advance as possible and start production as soon as is practical. Heavy copper boards, again, require extra time to process. There's no way to rush the production cycle for delayed release. And understand that these boards have cost structures that are, to varying degrees, significantly higher than standard boards. They're not suitable for every application, but when reliability is critical, they are often the best solution because they are very durable, very robust. And resources that we can offer obviously discussion. We can supply trace widths and spacing guides, current charts, and advice on best options and best practices, so that you don't get yourself painted into any corners. We can see where the project is going, and we can help you to avoid pitfalls by reviewing it early and often. So in summary, our heavy and extreme copper boards offer reliability in these critical military and aerospace applications. We can offer solutions that are manufacturable and repeatable, that's very important, based on our experience with a wide variety of applications. And we encourage you to engage with EPIC early in your project to discuss options for a successful experience. And with that, I'm going to hand it back to Kendall Paradise to discuss some of our other projects. We've received some questions, and I'll be looking through those for a few that I can answer during the allotted time. And so when Kendall's done talking, I will come back on and I will answer a few of those questions. Kendall?
Thanks, Al. As Al said, while he's going through some of your questions, we wanted to give you guys a quick overview of some of our other products and capabilities. As we went through today, all of our products have very specific product managers and manufacturing locations. But before we get to that, EPIC is a manufacturer of custom build-to-print electronics, including custom battery packs, fans and motors, custom cable assemblies, flex and rigid flex PCBs, and user interfaces and membrane switches. And as we just talked about, printed circuit boards, both of the lower technology variety and the higher copper mill aerospace applications that Al is talking about. If we go to the next slide.
Okay.
For each of these product lines, we have design centers and technical support with its own product manager dedicated to that specific area of expertise. Included in that, our battery pack and power management is located in Denver, Colorado. Our user interface is located in Largo, Florida. Our fans and motors is located here in New Bedford, Massachusetts, as well as our design center and testing center in Wales in the UK. For printed circuit boards, it's here in New Bedford, Massachusetts, as well as in Shenzhen, China. For flex and rigid flex, we're based out of Toronto, Canada, and our cable assemblies are also based out of Largo, Florida. As with Al, all of our resources are always ready to help with our customers. As Al said many times, earlier on in the project is always better for us to help you achieve the results that you're trying to get as quickly as possible. So with that, I'm going to thank you all for joining us today and turn it back over to Al to answer some questions.
Okay. Let's check these, and what would be a good one to start with? Okay, one question. Do you have any information about the effects of various materials or other factors that affect reliability? And the answer to that is yes. I actually did a presentation on, specifically on the reliability of plated through holes in heavy copper applications. And one of the topics it did touch on was the CTE of the laminates versus the CTE of the copper, and how when they're mismatched, that can lead to whole wall failures. And there are some materials that have CTE that's matched better to copper than FR4 is, but there's also another strategy is to use heavier copper plating in the hole itself. If you go to 2-ounce copper versus 1-ounce copper, you get a really significant drop-off in things like corner cracking in the holes. So I could supply a link to that. I believe that is probably up on our website, but I can find the link to that, and if you're interested, if anybody's interested, I can distribute that link. Okay, if I just want a budgetary quote to see if a project is feasible, do I still need to create documentation such as a concept drawing? The answer to that is no. For a budgetary quotation, where you're just trying to see whether you're going forward with a project or not, or whether it fits within your budget, we can do that through discussion. I generally capture the information that's relevant to the cost, the board size, copper weight, etc., what you're trying to do with your design, and we can generally do it that way. It's not quite as accurate as having things like Gerber files and drawings, because so much of a part of the cost structure on these boards is the copper pattern area. In other words, how much of the board is actually copper plated. That drives the copper plating time. The area drives the copper plating time. So we don't get quite as accurate a cost structure, but we can give you a pretty good ballpark idea so that you know whether you want to go forward or not. What's the other one here? Now this one's fairly easy, I guess, but most of the boards in the presentation use a gold surface finish. Is there a reason for that, or are those just the boards that happen to be photographed? Okay. Yeah, ENIG tends to be the best surface finish for these. We can also do things like immersion silver. We tend to shy away from hot air solder leveled tin lead. There is one board in the presentation that used one or two, but we don't like to use it on heavy copper because the copper stands so high off the surface that after the board gets dipped in the solder and the excess solder is supposed to be blown off the board, the high copper actually interferes with the action of those air knives, and you tend to get significant puddling, and sometimes you can even get bridging or almost like drops of solder. And for that reason, if we go much above like 6 ounces or so, we generally don't like to use hot air solder level. And ENEG also has advantages in that it's a very flat surface, and for that reason we've found that a lot of boards, it's the best for a lot of boards. It's the best solution. And I think I'll do one more of these. Let me see, in the slide about cost adders, you mentioned that one adder was the need to add extra plies of pre-preg. Could you explain that more fully? All right. Most pre-preg sheets, regardless of style, regardless of what their weave style is, that they cost approximately the same. And for that reason, fabricators like to use as few plies of pre-preg as possible. Now on normal boards, that's not a big issue because the copper circuitry doesn't really stand very high off the surface of the substrate, so you don't need a whole lot of resin to flow in order to seal all the gaps and prevent voids. So for like a 4-layer board, a fabricator might use like a single sheet of 76/28, which is 7/1000 of an inch thick. Well, to get that same 7/1000 of separation between 2 heavy copper layers, the copper on those heavy copper layers is much thicker, and the drop-off down to the substrate might be a right angle. So you're needing to fill that right angle with resin, or else you're going to get voids, and you're dealing with a high-power application to begin with. So you don't want anything bad to happen when that void heats up. It could blow, and that's not a good thing. So what you want to do is you want to use pre-preg that has a lighter glass style and a higher percentage of resin, and that way the glass can conform to drop-offs like that around the knee of a trace, and the resin flows more readily to fill the gaps. Now there are other things you can do too. You can also pre-fill the layers so that before lamination you pre-fill each layer, and then you planarize it down to the level of the copper, and then you can get relatively thin separations between the facing copper layers after that. That obviously adds a lot of cost and a lot of extra processing, but it's a thing that's used sometimes in particularly planar transformers where it helps prevent the layers from swimming around when they get laminated together. And it also, again, allows you to have a very thin and very predictable separation between one layer and the other when they're facing each other. So you end up with more sheets of pre-preg of thinner glass, higher resin when you're using heavy copper as a precaution, so that the board will be reliable and you won't get failures based on voiding. With that, I think we'll cut off the presentation at this point, and I will be addressing any other questions that we received by email. And I thank everybody for their time, and that should conclude the presentation. Thank you, everybody.